Please wait for some time. Actually, the thing is, yesterday I announced that 6:30 to 9:30 class is there, but the office people they created that 6 to 9:30. Okay, so there is a little bit confusion, right? So let us wait for some time, right? We'll starting at 6:30. Okay. Is my screen visible to all? Right. Yes, 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 yes. Okay, okay, okay. Yes. Sorry, actually, there is a little bit confusion regarding the whether the class will start at 6:30 or 6. Okay. In the portal, it was showing 6 to 9:30, and yesterday, actually, during session, I announced that it is from 6:30 to 9:30. Okay. So, anyways, those who joined earlier, right? Sorry for inconvenience, right? So let us first revise the yesterday whatever we discussed, and after that we'll be proceeding towards the today's topics, right? So yesterday we started the three-phase rectifiers. As I said, in a three-phase rectifiers, we are having a three-phase three-pulse uncontrolled rectifier, three-phase three-pulse controlled rectifier, right? Three-phase six-pulse uncontrolled and three-phase six-pulse controlled rectifier. And apart from that, we'll be discussing the three-phase semi-converters as well, right? So in a three-phase half-wave uncontrolled rectifier, yes, we are having the circuit like this only. The only thing is these three thyristors will be replaced by a diode. Okay, so instead of T1, T2, T3, in that circuit, if you recall, we were having the D1, D2, and D3. Specifically here, we require 4 wires, right? 4 wire supply. So that's why the transformer secondary should be connected in star only. Then and only then it is possible, right? Next. So if you recall, for three-phase, yes, uncontrolled diode rectifier, here the respective diode will be in a conduction mode if the across that diode the voltage will be higher compared to that of the other two diodes. So accordingly, here from pi by 6 to 5 pi by 6, that is for 120-degree, it is like a diode D1, okay, will be in a conduction mode. So when D1 is in a conduction mode, output voltage is equal to VAN. That thing we discussed. Next, from 5 pi by 6 to 9 pi by 6, output voltage is diode D2 will be in a conduction mode because VBN will be maximum compared to that of remaining two voltages, right? So therefore here, yes, during when D2 conducts, output voltage is equal to VBN. So therefore, when D2 conducts, that is from 5 pi by 6 to 9 pi by 6, in the output, we are getting the VBN. Similarly for VCN, that is for 9 pi by 6 to 13 pi by 6. Okay, 13 pi by 6 means it is like a 2 pi plus 30-degree. Na? So 2 pi means one complete cycle of the supply will be here, right? So in the output, we'll be getting this type of waveform. So this point is like alpha equal to 0 degree for thyristor. Na? We discussed the same point, right? Because the diode rectifier and the thyristor rectifier, the difference is if we keep alpha is equal to 0 degree for a thyristor rectifier, then we'll be getting the waveform which is similar to that of a diode rectifier. Okay. So next, if the load is RL load, we'll be getting the constant waveform. We'll be getting the constant waveform, right? After that, we have derived the expressions V0 average, V0 RMS, I0 average. Okay. Apart from that, we can draw the waveform of IA or ID1 also. Okay, IA or ID1 also. Okay. If they ask what is the value of ID1 average, suppose for the RL load, if this is a ID1, what is the ID1 average? If we want to find, if yes, in that case, we need to check during which interval the diode D1 is in a conduction mode. So here diode D1 is in a conduction mode only from pi by 6 to 5 pi by 6. Okay. So how will the waveform of ID1? ID1 waveform should be, it will be same as that of the load current during interval pi by 6 to 5 pi by 6. For remaining all angles, it will be 0. Yes or no? Right? Next, from that we can find the I0 average, ID1 average, IA average, etc. Okay. So please keep it in mind. If we want to find the respective switch current waveform, okay, then we need to check first during which interval that switch was in an on state, and when the switch was in on state, then through that switch which current was flowing. Okay. So yes, accordingly we can draw the waveform for IB as well as IC also. Okay, that is phase B current, phase C current as well, right? IA means this current. In the numericals, we will discuss. If it requires, we can will be drawing there. Okay, next. Yes, three-phase half-wave control rectifier. In the control rectifier, we have replaced the diodes with the thyristors. Thyristor is a controlled switch, we know. Okay, so yes, here these points are important. Alpha equal to 0 degree for thyristor T1, alpha equal to 0 degree for thyristor T2, alpha is equal to 0 degree for thyristor T3. How we identified these points? If you check the continuous conduction, okay, as I said, at a time only one thyristor will be in on state, right? So definitely before T1 there was a thyristor T3 will be in a conduction mode, yes or no? So when T3 is in a conduction mode, in the output will be getting the voltage is equal to VCN, okay? And when T3 is in a conduction mode, let me indicate here, when T3 is in a conduction mode, suppose only T3 is in a conduction mode, then here it is a neutral point means 0 volt. Consider this voltage will be your VCN na? If this is VCN, here it is VCN, here voltage is a VCN. Next, the same VCN will appear here, same VCN here, same VCN here. So when T3 is in a conduction mode, at the cathode of thyristor T1, the voltage appearing is VCN. At the anode of thyristor T1, the voltage appearing is VAN. Okay. So now, unless and until your VAN becomes greater than VCN, our thyristor T1 will not turn on. Yes or no, right? Or will not become the forward bias. So you can check here. After pi by 6, VAN is greater than VCN. VCN means this blue line. Okay, right? So after pi by 6, VAN is greater than VCN. So can we say that the voltage across thyristor T1 will be greater than that of the voltage across voltage at the anode of thyristor T1 will be greater than that of the cathode voltage only after this instant pi by 6. Okay, so that's why we indicated alpha equal to 0 degree for thyristor T1 here. Similarly, when T1 is in a conduction mode, at that time the remaining two thyristors, will be in a off state. Okay, means T3 is in a off state. Yes, T1 will be in a conduction mode. Okay, when T1 is in a conduction mode, at that time T3 will turn off, T2 is also in a off state. Okay, so therefore, if it is VAN, definitely it is a VAN because T1 is acting as a short circuit na? So it is VAN means here it is VAN, here it is VAN, here it is VAN. Okay. So you can check the voltage at the anode of thyristor T2 is VBN, voltage at the cathode of thyristor T2 is VAN. So unless and until VBN becomes greater than VAN, yes, our thyristor T2 will not switch into the forward bias mode. So you can check the instant where VBN is greater than that of VAN means this 5 pi by 6. So that's why we indicated this is like alpha equal to 0 degree for T2. Similarly, we have written alpha equal to 0 degree for thyristor T3. Okay, so these are the alpha equal to 0 degree for T1, T2 and T3. So that's why we written here. For T1 alpha 0 means omega T is pi by 6. Means if I want to keep firing angle 0 degree, okay, for my circuitry, then I need to trigger thyristor T1 at pi by 6. I need to trigger thyristor T2 at 5 pi by 6. I need to trigger thyristor T3 at 9 pi by 6. It is not like that. Alpha 0 means at omega T 0, we are triggering all the three thyristors. No, right? So alpha 0 degree for thyristor, each thyristor means T1 is omega T pi by 6, T2 is omega T 5 pi by 6, T3 is omega T 9 pi by 6, right? So here we have discussed the concept. First is for alpha less than 30 degree, and also we discussed for alpha equal to 30 degree as well. Okay, so for alpha less than 30 degree, the meaning is we need to measure the firing angle of thyristor T1 from omega T is pi by 6. Okay, so if omega T is pi by 6 means alpha equal to 0 degree. Okay, now suppose if I want to maintain the alpha is 15 degree, alpha is 15 degree, 15 degree, then this pi by 6 means alpha 0 degree for thyristor T1. Okay, so in that I need to add 15 degree. In that I need to add a 15 degree. Okay, so you can check pi by 6 plus 30 degree means this pi by 3 instant. Okay, so pi by 6 plus 30 means this pi by 3. So pi by 6 plus 15 degree means somewhat in between these two now. Okay, so that's why this point we have indicated. At this point, what we have done? Yes, at this point actually we have triggered the thyristor T1. We have applied the gate pulse to thyristor T1. So you can check from here. I can measure the angle between these 2 points, and that is nothing but my firing angle alpha for the thyristor T1. Similarly, same firing angle we need to maintain for thyristor T2 as well. So for thyristor T2, alpha equal to 0 degree means 5 pi by 6. So same 5 pi by 6 point is here. Okay. So after that, after 5 pi by 6, we need to add 15 degree. So after 5 pi by 6, if I add 15 degree, the point will be here. Means at this instant, I am triggering thyristor T2, right? Similarly, omega t is 9 pi by 6. Omega t is 9 pi by 6 is nothing but alpha equal to 0 degree for thyristor T3. In that, we need to add a 15 degree more, means this point will come. Okay. So we are triggering or we are applying the gate pulse to thyristor T1 at this instant, thyristor T2 at this instant, thyristor T3 at this instant. Okay. But in continuous cycle, if you check before T1, definitely T3 will be in a conduction mode. I'm saying in continuous cycle, because it is a continuous process. T1 conducts, after that T2 conducts, after that T3 conducts, again T1, again T2, again T3, again T1, T2, T3, means this cycle, this loop go on repeating, right? So here you can check, here we are triggering thyristor T1. So before that, definitely T3 will be in a conduction mode. Okay. So when T3 is in a conduction mode, in the output, which waveform will be getting? When T3 is in a conduction mode, in the output will be getting V0 is equal to VCN only. Simply you can apply KVL to this loop. It is a plus VCN minus V0 is equal to 0 na. Plus VCN minus V0 is equal to 0 means VCN is equal to V0, right? So here in the output, yes, we're getting the V0, which is same as that of the VCN, the blue line. Okay. So same waveform we are getting here. Next, but this will continue only till we apply the gate pulse to thyristor T1 na. At this instant, we are applying the gate pulse to thyristor T1. So you can check corresponding to this instant. VCN is a non-zero value na. Corresponding to this instant, the VCN is a non-zero value. So that's why our V0 will be reaching, or the V0 will be same as that of the VCN, means will be non-zero till the instant we apply the gate pulse to thyristor T1. At this instant, I am applying the gate pulse to T1. So what will happen? As soon as we apply the gate pulse to thyristor T1, so T1 will act as a short circuit. When T1 acts as short circuit, means voltage here is VAN, here it is also VAN, because it is a short circuit na. So potential difference across T1 is 0. So whatever potential at the anode, same potential will appear at the cathode. So this VAN is nothing but this is VAN. Here it is VAN, here it is also VAN. Now you can check when T1 turns on, what will happen to T3. Okay. So once T1 turns on, at the cathode of T3, the voltage is VAN. At the anode of T3, the voltage is VCN. Okay. So you can check anode voltage is VCN, cathode voltage is VAN. Now at the instant of triggering of thyristor T1, check the value of VCN and VAN. If VCN is less than VAN, can we say that thyristor T3 will be reverse bias? Okay. So please check at the instant of triggering of thyristor T1 means this instant. Okay. At this instant, you can check VAN is greater than that of VCN. Okay. So VAN is greater means cathode voltage of thyristor T3 is greater than that of anode voltage, means thyristor T3 will be in off state now, right? So therefore, once T1 turns on, your T3 will turn off. Okay. So now T3 is in off state, means in the circuit we will be having only thyristor T1 is in a conduction mode. So current will be flowing from VAN, T1 load, and again back to the neutral point. In this loop, the current will flow now. So what is the V0? V0 is equal to VAN. So you can check here. Yes, V0 is suddenly at the instant of means as soon as your thyristor T1 turns on, na, thyristor T1 acts as short circuit, your output voltage will suddenly jump from VCN to the VAN value. You can check here. Initially, it was a VCN only. When thyristor T1 turns on, the output voltage will suddenly jump from this point to this point. Okay. So that's why there is a sudden increase in the output voltage. After that, the output voltage will be same as that of your VAN value as it is. This will continue till we apply the gate pulse to thyristor T2. Okay. We're applying the gate pulse to thyristor T2 at this instant. Now we're applying the gate pulse to thyristor T2 at this instant. Okay. So till this instant, the output will be like a VAN only. Now you can check at this instant when we apply the gate pulse to thyristor T2. But before that, please check whether our thyristor T2 will be forward bias mode or reverse bias mode. Okay. So you can check corresponding to this instant. Yes. When the thyristor T1 was conduction mode, at the cathode of thyristor T2, the voltage appearing was VAN. Okay. Anode voltage is VBN, cathode voltage is VAN. Okay. So what is the voltage across thyristor T2? It is a VBN minus VAN. Now at the instant of triggering of thyristor T2, please check the value of VBN and VAN. Okay. VBN and VAN. At the instant of triggering of thyristor T2, I am saying. So at the instant of triggering of thyristor T2 means this point. This point is nothing but this point here we are having. Okay. Corresponding to this point, you can check VAN is here and VBN is here. So can we say that VBN is greater than VAN? So if VBN is greater than VAN means anode voltage is greater than that of the cathode voltage. The meaning is anode voltage greater than cathode voltage means thyristor T2 is in a forward bias mode, and we are applying the gate signal to that thyristor. So whether our thyristor T2 will turn on or not, definitely thyristor T2 will turn on. Okay. So now, yes, conclusion is at this instant thyristor T2 turns on. So when thyristor T2 turns on, what will happen to thyristor T1? Let us discuss, because initially T1 was in a conduction mode now, right? So as soon as T2 turns on, yes, the voltage that is appearing at the cathode of thyristor T2, you can check here. It is VBN means definitely here it is VBN. Same VBN will appear here. Same VBN will appear here also, right? So now you can check the thyristor T1. Anode voltage is VAN, cathode voltage is VBN. Okay. So when T2 turns on, at that instant, check the VAN and VBN values. Yes, when T2 is turning on at this instant means this instant. Okay. Corresponding to this instant, VAN is less than VBN. If VAN is less than VBN means thyristor T1 anode voltage is less than cathode voltage. So can we say that thyristor T1 is in a reverse bias mode? Yes or no, right? So thyristor T1 is in a reverse bias mode means it will turn off immediately. Okay, it will turn off immediately. So as soon as T2 turns on, your T1 will turn off. So when T2 conducts, that is T2, when T2 is in on state, current will flow from VBN, T2 load and again back to the VBN. Okay, in this loop the current will flow. So what is V0? V0 is equal to VBN, right? So you can check in the output will be getting the VBN. In the output will be getting the VBN. This will continue till the instant we apply the gate pulse to thyristor T3. We're applying the gate pulse to thyristor T3 at this instant. Okay, we're applying the gate pulse to thyristor T3 at this instant, na? This instant. So before that, in the output will be getting VBN only. Okay. Now you can check at this instant when the thyristor T3 turns on, or before that, please check at this instant whether thyristor T3 will be in a forward bias mode or reverse bias mode. Okay. You can check here, because when T2 is in a conduction mode, the voltage at the cathode of thyristor T3 is VBN, anode voltage is VCN. So check the VCN and VBN value at the instant of triggering of thyristor T3. Okay. VBN and VCN value, VBN and VCN value at the instant of triggering. So instant of triggering means nothing but this point here. At this instant, you can check VBN is this much, VCN is this much. Na? At this instant, you can check VCN is here, VBN is here. So VCN is greater than VBN. So if VCN is greater than VBN means anode voltage is greater than the cathode voltage. So definitely thyristor T3, yes, is in a will be in a forward bias mode. Okay. So when T3 is in a forward bias mode, and if we apply the gate signal to thyristor T3, definitely our thyristor T3 will turn on. Okay. Similarly, you can check once T3 turns on, your thyristor T2 will turn off. You can check it. Okay. How it will turn off. The same thing whatever we discussed earlier. So when T3 turns on, here voltage is VCN, here voltage is VCN, here voltage is VCN. Okay. So as soon as your T3 turns on, T2 definitely will turn off, because this VCN will be greater than that of VBN. Okay. So how current will flow? Current will flow from VCN, T3 load and again back to the neutral point, right? In this loop, the current will flow. V0 is equal to VCN. So you can check when T3 turns on, V0 is equal to VCN. Okay. So you'll be getting this type of waveform. Again, the important thing you can check, 2 pi means this here. 2 pi means this instant, na? So 2 pi is like the 0 only, na? 2 pi means one complete cycle of the supply. So again, it is like a 0 only. So whatever the waveform we are having from 2 pi to 13 pi by 6, na? This same waveform will be appearing from 0 to this instant. Are you getting the point, right? So same waveform. So if you compare this waveform and diode rectifier waveform, yes, you will understand in the diode rectifier waveform, yes, we were having, yes, in the diode rectifier waveform, either it is R load or RL load, right? Waveform, it will not change. Let me show it for R load first. Okay. How was the waveform? It was from this point, it was increasing slowly, na V0, decreasing slowly, and from the same point again it has started increasing. Means there was no yes, sudden increasing was not present here. Okay, in the case of diode rectifier, I'm saying. But whereas if you check this waveform, here we are having a sudden increase. Here we are having a sudden increase from this value to this value, from this value to this value. We are having a sudden increase. Are you getting the point? Okay. So this is when alpha is non-zero. For thyristor rectifier, if I keep alpha equal to 0 degree, what will happen? Alpha 0 degree means I need to turn on thyristor T1 at omega t pi by 6, na? Alpha 0 degree for T2 means I need to turn on thyristor T2 at 5 pi by 6. Similarly, thyristor T3 at 9 pi by 6. Okay. So indirectly we'll be having from this instant only we'll be getting the output is VAN. So whatever the waveform of diode rectifier, okay, we discussed the same waveform we'll be getting when alpha equal to 0 degree in thyristor rectifier. Okay. Next. Now suppose yesterday we discussed same I0 will be in phase with V0 because load is purely resistive. Now suppose if we keep alpha equal to 30 degree, then what will happen? That thing also we discussed. Alpha 30 degree means we need to apply gate pulse to thyristor T1. Okay, gate pulse to thyristor T1 at this instant, and this instant is nothing but pi by 3. Okay, you can check. Alpha 0 degree for thyristor T1 means omega T is pi by 6. If I want to keep the alpha 30 degree, means in this angle I need to add again 30 degree na. So omega T is pi by 6 plus pi by 6, that is a pi by 3. So your omega gate pulse is at pi by 3, we need to apply the gate pulse to thyristor T1. Similarly, alpha 30 degree means we need to apply the gate pulse to thyristor T2 at pi radian. Alpha 30 degree means we need to apply the gate pulse to thyristor T3 at 5 pi by 3 radian. Okay, so now you can check when gate pulse is applied to thyristor T1 at this instant. Before that, definitely T3 will be in a conduction mode. When T3 conducts, in the output the voltage waveform will be VCN. You can check here. So till pi by 3 in the output will be getting the VCN waveform. So at pi by 3 you can check VCN is reaching the 0 value. So in the output will be getting the, it is like VCN same shape and it is reaching the 0 value. And as soon as it reaches the 0 value, I am turning on thyristor T1 now. So definitely your output voltage will change from this point to this point now, from this point to this point. So that's why there is a large sudden change you can observe. Okay, from 0 to the non-zero value. Similarly, here also sudden change, here also sudden change. So for alpha less than 30 degree, it is like output voltage will be non-zero for all the time. It is not reaching the 0, right? Whereas if you check alpha equal to 30 degree, your output voltage is reaching the 0 value. Output voltage is reaching the 0 value, and from the same point, it is again jumping to the non-zero value, right? So this is for alpha equal to 30 degree. Now suppose if alpha is greater than 30 degree, what will happen? Let us discuss. Okay, if alpha is greater than 30 degree. So let me write, if alpha is greater than 30 degree, what will happen, right? So this is your supply voltage waveform, right? Omega T. This is your VAN. Here it is a VBN. Here it is a VCN, right? This indicates pi by 6. This is pi by 3, pi by 2, 4 pi by 6, right? And this is like your 5 pi by 6. This is a pi by 3 instant, right? Next, 5 pi by 6. 6 pi by 6, that is a pi. 7 pi by 6, 8 pi by 6, this is a 9 pi by 6. 10 pi by 6, this is like 10 pi by 6 means 5 pi by 3. 11 pi by 6, 12 pi by 6, 13 pi by 6, right? This is like your 2 pi radian. Okay, this instant is 2 pi radian. Now let us discuss what will happen if we keep alpha greater than 30 degree. Okay. We are discussing the R load. R load. Yes, alpha 30 degree means what is omega T for thyristor T1? Come on. If alpha is 30 degree means what is the value of omega T for thyristor T1? Alpha 30 degree means omega T is, if alpha 30 degree, then omega T means, come on. Yes, Salman Khan, correct. It is a pi by 3. Mukul, you are saying pi by 6. How? Yes, alpha 0 degree means omega T pi by 6 na, we have written. So alpha 30 degree means we need to, alpha 30 degree means omega T is pi by 3. Yes or no? Means in this angle, we need to add 30 degree more. Okay, so if alpha 30 degree means omega t pi by 3. So for alpha greater than 30 degree means we need to apply the gate pulse to thyristor T1 after pi by 3 na? Yes or no, right? So suppose I am applying the gate pulse to thyristor T1 at this instant. Okay, yes, at this instant I am applying the gate pulse to thyristor T1. So what this point indicates, this total indicates your alpha. Yes or no, right? You can check from this point to this point, this is a 30 degree, right? And again 30 plus this angle, so that's why it is a greater than 30 degree. Similarly, alpha 0 degree for thyristor T2 means omega t is 5 pi by 6. In that, if I add 30 degree, then I will be reaching pi radian. But if we are we need to keep the alpha greater than 30 degree means we can apply gate pulse to thyristor T2 here. So this is your alpha. Yes or no? Similarly, the gate pulse to thyristor T3 9 pi by 6, omega t 9 pi by 6 means alpha 0 degree. Okay. In that, if I add 30 degree, then I will be getting 5 pi by 3. But alpha is greater than 30 degree means I need to apply the gate pulse. Yes, after 5 pi by 3. So this is the alpha for thyristor T1, T2, and here it is a T3. Is this clear? Right? So please try to understand. Unless and until you understand this, how to select, how to find that corresponding alpha, what is the value of omega t for that alpha, right? You will not draw, you cannot draw the waveform, right? So here I am repeating, omega t pi by 6 means alpha 0 na. So we are interested in alpha greater than 30 degree means after this point I need to add greater than alpha angle greater than 30 alpha, which is greater than 30 degree. So that's why firing angle will be at this point. Okay, that is the gate pulse we are applying. Next, for thyristor T2, omega t 5 pi by 6 means nothing but alpha 0. If alpha is greater than 30 degree means we need to apply the gate pulse to thyristor T2 here. Okay. Similarly, for thyristor T3, we need to apply the gate pulse here. Okay. So now let me, yes, right here. On this instant, let me take the projection first here. Right. So here it is like our thyristor T1 will turn on here, thyristor T2 here, thyristor T3 here. Right. Now you can check at this instant our thyristor T1 will turn on because we are applying the gate signal. But before thyristor T1, which thyristor was in a conduction mode? It is like thyristor T3. When T3 conducts, means before this instant I am saying, when T3 conducts, in the output, which waveform will be getting? VCN waveform. Yes or no? Right? So when T3 conducts, you can check before this point. Okay, before this point, if T3 is in a conduction mode, in the output will be getting the VCN waveform. So you can check the VCN waveform. In the output will be getting the VCN waveform, but the VCN is non-zero or positive only till omega t is pi by 3. After pi by 3, what is VCN? It is a negative, na? Right? So check here, VCN will be positive as it is here till pi by 3. And this point is like a pi by 3. Now after pi by 3, VCN is negative. So let us check what will happen when VCN is negative. What will happen when VCN is negative? So please try to understand. From this point to this point, it is like thyristor T3 was in a conduction mode, so output voltage is equal to VCN only. Okay, so now you can check when T3 is in a conduction mode, coming toward this circuit, when T3 is in a conduction mode. Okay, T3 is in a conduction mode, so it is like a VCN here, here it is also VCN. Okay, so at that time your T1, T2 will be definitely reverse bias mode. Okay, they will not turn on. Now the question is VCN after pi by 3, VCN is switching into the negative values. After pi by 3, VCN is switching into the negative values now. So if VCN is switching into negative values means what? This voltage will be negative now. This VCN is negative. VCN negative means what? The polarity will be plus here and minus here. Now you can check. Now you can check. This lowest potential point will appear at the anode of thyristor T3. Highest potential point will be appearing at like a cathode of thyristor T3. So when VCN becomes negative, whether our thyristor T3 will continue into the conduction mode or whether it will turn off. Are you getting the point? When VCN is negative, whether thyristor T3 will continue into the conduction mode or whether it will turn off due to the reverse voltage. Definitely it should turn off now, because this voltage VCN is reversed, means what? Here it is plus, here it is minus now. Lowest potential is appearing at the anode of thyristor T3 na. So please try to understand. Yet we have not applied the gate pulse. Yet we have not applied the gate pulse to thyristor T1. So that's why only thyristor T3 was in a conduction mode. But that too till pi by 3 you can check. Till pi by 3 VCN is positive, so no problem. Our T3 will definitely conduct. But after pi by 3 VCN is negative. So that's why at omega t is pi by 3 or after pi by 3, just after pi by 3, as VCN is negative, our thyristor T3 will immediately turn off. So when T3 turns off, yes, we'll be having the circuit like, suppose T3 is also turning off. So now you can check at omega t is pi by 3, our thyristor T3 is turning off, means at this instant thyristor T3 is turning off. So you can check from this point till the instant we apply the gate pulse to thyristor T1. From omega t is pi by 3 till the instant we apply the gate pulse to thyristor T1. It is like none of the switch will be in a conduction mode now, because yet T1 is not turned on, T2 we are not applying the gate signal, right? And T3, due to the reverse voltage, T3 has turned off. So it is like all the three switches will be in an off state. So if all the three switches are in off state, whether the current will flow from source towards the load? No. So what is V0? 0. What is I0? I0